In this module, we will be looking at thermal performance of building envelope. I will be teaching about the fundamentals of heat transfer through building envelope, and I will be showing you some applied examples in which we will be looking at how these principles are applied in specific buildings. Let us take a look at this particular image. There is a cross section of a wall. It can be any material. For now we are not getting into what are the thermal and physical properties of this wall. There is a cross section. Imagine it is 200 mm thick wall, and here what you see is the timeline. It starts from 12 o'clock on a particular, this is a night, 12 o'clock, then it goes on to the 1 day cycle, 24 hours, and then this is a second day. So there is totally 48 hours covered here, starting from 12 in the night goes on to 24 hours, that is the second day. What we are trying to show is a heat build up, heat transfer, and then heat re-emission, that is how the wall is getting heat in and how it is letting heat out of the building. So this is outside and this is inside of the building. Let us start looking at somewhere from this point, say take about 8 o'clock, where you start getting, imagine this is a east facing wall. It can be any surface, later we will look at the details, but imagine this is a east facing wall. You start getting solar incidence somewhere around 6:37 in the morning, it depends on the season as well. So imagine you get some solar incidence here, then this wall starts getting heated up. What happens? There is a heat built up. This, the depth of this bars show how much amount of heat is getting built up. So there is a heat build up here. Then depending on the thermophysical properties of the wall is going to store some amount of heat and then pass some amount of heat into the room. So this process takes a while, that is the solar radiation needs some time to heat up the wall, then it needs some time to pass through this particular distance, say now it is 200 mm. Then after a while you start getting or realizing, say when there is a initial heat build up, you do not see anything here. Say if you apply heat here, if you touch this surface, immediately you are not going to feel anything. So after about an hour, that is what we have tried depicting here, after about an hour or slightly more in this particular wall, it depends again how insulative the wall is. We are going to look at this precisely in this module. After a while you start getting the heat passing into the built surface, that is into the room. So there is a peak here, this particular peak, after say 1.5 hours you get the peak inside. The magnitude may be different, that is why the colors are different. Now you are getting heat into the pumped into the built space. So after this heat source is gone, that is after the sun has gone to the other side of the building or after the sunset, this particular wall, now there is no heat source, eventually it starts minimizing the intensity of inward heat pumping. So after this there is a reverse phenomena, the magnitude is not the same. If you look at this, there is a good amount of heat gain, whereas the reverse process it is pretty less. So what happens here, there is a eventual reverse flow of heat. Similarly this takes a while, and after this particular time the wall also loses heat to the ambient. The same phenomena, if you look at any particular surface, there is a heat build up, second day there is a heat build up, there is a heat loss, and this is for the third day, there is going to be the heat loss. Inside similarly during the daytime, later in the day there is a heat gain, and then again the second day, later in the day there is a heat gain. So this particular peak to peak, this is what is of interest to any building designer. Now we are going to look at how these mechanisms work and what are the fundamentals behind it. Just brushing up the basics what we studied in school, there are three modes of heat transfer: conduction, convection and radiation. Heat flow depends on the temperature difference, that is delta T, what happens on one side of the wall, what happens on the other side of the wall, what is the ambient temperature, what is the indoor temperature. Say if you air condition your room, for the same summer day the heat transfer is going to be different, whereas if you leave the building in a free running mode or unconditioned or naturally ventilated mode, then the heat transfer is going to be different because the delta T is different. Then it depends on the surface area, how much wall surface or how much window surface or what is the integrated surface area which is exposed between the two temperature differences. Outside is 45 degrees, inside is say 24 degrees set point temperature. So you have about roughly 21 degree difference, that is a delta T. Then you have this much amount of wall area, say for example a 4 meter long, 3 meter high, 12 meter square of wall area, probably you have about 10% window wall ratio in that. Then in that case this is a amount of wall surface which is involved in the heat exchange. Then it depends on the distance travelled, say a thick surface or a thick wall versus a thin wall. It depends on the distance travelled, and then it depends on the surface characteristics, whether the surface is reflective, whether it is absorptive, emissive. These are few properties that is of interest to us, which we will be looking more closely in this particular module. Two bodies are in thermal equilibrium when they have same temperature, that is, say you have a chamber, both sides it is 25 degrees, then this particular wall or a particular solid is said to be, or any fluid is said to be in thermal equilibrium. So these two sides there is no heat transfer which is happening. Naturally heat flows from the hotter side to colder side. These are basic principles which we already know. If it has to happen from the other side, you need a heat pump. First let us take a look at conduction. It is a transfer of heat when two particles or two bodies are directly in contact with each other. A hotter surface is in touch with the colder surface, then you start realizing the conductive heat transfer. Looking into the microstructure, what happens within a body, like we saw the wall case, one side is getting heated up, eventually there are smaller particles which are getting in touch with each other, they are getting excited, and then because of that direct contact there is a heat transfer happening from one side of the other. This particular heat transfer or the efficiency of conductive heat transfer is primarily dependent on the amount of air trapped into this particular material. We can refer it in terms of porosity, or indirectly we can refer it in terms of density, that is how porous a material is. Take a dense steel sheet. The material is really dense, the particles are so compactly placed, the density is high, porosity will be pretty minimum, then the heat transfer is going to happen much faster. On the other hand, you take a like a glass wool, a material like glass wool which is much internally the particles are much more dispersed, or you take a aerated concrete, foam concrete, where you have lot of air bubbles which are embedded into the concrete and cement paste basically. So in that case the heat transfer, the mode of heat transfer keeps changing. First the heat will encounter a cement block, then it will have an air void. So alternately it has to keep transferring from one medium to the other medium, and there are lot of losses because of this. So this particular air bubbles and embedding them makes a lot of difference in the conductive heat transfer. Typically solids are better conductors than liquids, and liquids are better conductor than gases. Typically we look at this in terms of insulated windows. Again when you go for rare gases like argon sealed windows, then the heat transfer, the conductive heat transfer gets further lower. Further about conduction, the conductive heat transfer depends more on the structure of the material than the material itself. Like precisely when I told you what happens with the glass block, the same material is used in a glass block which is commonly used for internal partitions and all that. You have a glass block, say 100 mm thick glass block, you have the same material. The mode of heat transfer, let us take just conduction for now. The amount of heat transferred through a glass block is going to be considerably more than through a fine fiber in the form of glass wool. This also has a similar material, but it is spun in the form of fibers. So the material remains the same, but the structure of the material or internal microstructure of the material more precisely is considerably different. There are a lot of air voids built, and the built of the structure itself is, microstructure itself is different. So because of this there is a considerable difference in conductive heat transfer. This is a very simple most commonly used equation where for heat load cooling load determination they use this equation pretty commonly in buildings. On one side you have Q, which is the conductive heat flow through opaque materials, which is equal to U. U is a transmission coefficient, we are going to look at this particular number more in detail. U, which is a heat transfer coefficient, conductive heat transfer coefficient, area of the surface, that I was mentioning about how much area is involved in the heat transfer, and the temperature difference delta T. So Q is expressed in watts, or you can cut it down to watts per meter square. If this area component is negated, you will have A U into A into delta T. This is what actually gives you conductive heat transfer. There are two other modes of heat transfer. This is primarily for how conductive heat transfer happens. So when we talk about conductive heat transfer, we have to in the process remember few terms and terminologies which are in field commonly more confusing because they sound similar. Some of the commonly used parameters, that is conductivity, conductance and thermal transmittance. These three parameters are quite frequently used, but they are more interchanged quite often confusingly. First let us take a look at what conductivity means. It can be expressed, commonly it is expressed as K, but the denotation can be anything. It is the heat flow through a material per unit thickness. So the first thing we have to understand is conductivity is a material's property. It is a inherent material's thermal property. It is not dependent on thickness, because thickness factor is negated here, it is per unit thickness whatever it is. So when we say conductivity of the material, it is expressed in watt per meter Kelvin. It is the amount of heat getting transferred from one side of the material to the other side of the material. It is commonly measured in laboratories. There are methods like hot plate apparatus, hot box apparatus. These are apparatus used for ASTM codes are available for these testing. I can tell you a few examples. For example, if you want to say test the conductivity of brick, you slice the brick, put them in between two plates, one is a hot plate, other is a cold plate. There are standards for setting these temperatures, dimensions, proportions. So from one side, the hotter side to the colder side, heat transfer happens, and how much amount of heat is getting transferred through this slice of brick is measured as its conductivity or the K value. As I said, it is expressed in watts per meter Kelvin. In hot box apparatus, you can test larger materials wall panels. There are two chambers. One chamber is a hot chamber, other is a cold chamber. So from one chamber to the other chamber, heat transfer happens. Hot box apparatus is more gives you more realistic estimates of heat transfer compared to hot plate, because it is more an idealistic condition, but it is easy to test materials. For say example, you want to know what is the conductivity of a thin glass sheet or conductivity of irradiated concrete block, then you can simply put it in hot plate apparatus, test it, you will know what is the conductive heat flow or the conductivity. The next parameter which is important is the conductance. Here this is the heat flow through a material for a stated thickness. Now we are starting to include the cross sectional thickness of the particular material. So here this is like conductivity K by x is a unit thickness. So the unit is watts per meter square Kelvin. So this is, for example, when somebody says conductance of a material, the first thing you should be asking them is for what thickness. Conductance for a 100 mm thick brick wall or 110 mm thick brick wall would be different from a 220 or 230 mm thick brick wall, because conductance is includes a factor of thickness here. As the material gets thicker and thicker, the conductance value is going to come down because thickness is in your denominator. Thermal resistance, countries like US, they don't refer to conductivity and conductance or the transmittance value, rather they talk about R value or the resistance value. It is a inverse of conductance. Actually this plot, I have plotted in x axis you have density of different material. These are common construction material. It states it starts from very low density material like glass wool or insulation material, and it goes as high as 2500 thick dense concrete kind of material. I have taken different density materials which are commonly used for building envelopes. It can be solid opaque structural material versus insulation material from one end to the other end. Here you have the thermal conductivity, watt per meter Kelvin, conductivity not conductance. There is a strong relation between density of a material and conductivity of a material. As the density increases, there is a proportional increase in conductivity. I won't say density is the only factor determining thermal conductivity. There are other properties, and it is directly proportional in most of the cases. That is, most of the materials there can be differences. That is what actually you see. It is not like a linear relation, it is an exponential relation, but typically as the density increases for most of the construction materials used in building envelope, the thermal conductivity is going to go up. The next important parameter, or the most commonly used parameter term, is the U value. U value typically is referred as thermal transmittance, but more technically or more precisely it is air to air thermal transmittance. So you have a wall surface. If you carefully look at the cross section, what are all the cross sections through which, cross sectional elements through which heat is going to get transferred? The most common thing take a brick wall. 210 mm thick brick wall with 10 mm plaster on both sides. Totally it makes it 230 mm thick. Now if you draw a cross section, it is going to look like this. You have a plaster, layer of plaster, then you have the brick layer, then you have the internal plaster. So there is a conductivity value for this, there is a conductivity value for this, and there is a conductivity value for this. And converse, you have the thermal resistance. On the reverse, you have a thermal resistance. But apart from this, there are two other parameters which are here, H naught and Hi. If you say this is outside and this is inside, then you have a thin layer of air film which is adhering to this particular surface, both outside surface as well as inside surface. Actually the resistance of this particular film has a quite a significant impact on the total conductive heat transfer from outside to inside. This particular film coefficient also depends on or primarily depends on the surface characteristics of the wall as well as the environmental condition. We will look at it more in detail, but now to quickly understand, there is K1 which on the reverse, if you include the thickness, say now it is 10 mm, this is 210 mm and this is another 10 mm. Together this is out, this is in, together this gets you a 230 mm brick wall, but apart from this you have a film coefficient out and film coefficient in. This exactly is what we are trying to look at. First we are trying to sum the R values, that is a thermal resistance on total, then we are taking a 1 by thermal resistance, 1 by sum of thermal resistance, which becomes your U value or air to air thermal transmittance. That is why we say, this is outside air to inside air, that is overall air to air thermal transmittance is what is referred as U value. The unit for U value is watts per meter square Kelvin, same as conductance. Take a close look at air films. You have an outdoor air film, you have an indoor air film. It is determined by the surface characteristics as well as environmental condition. There are lot of reference tables as well as formulas to calculate. Lot of people are conducting detailed research in this field, but for a simple understanding of the subject, there is a significant amount of variation in this film conductance outside as well as inside, for a rough surface versus a smooth surface, for a reflective surface or a emissive surface versus a less emissive surface. It also depends on what is the relative humidity outside. It also depends on how much air velocity, how much velocity of air is impinging on this particular surface. The film coefficient is going to be different when the breeze, when it is windy versus when it is a stale air. There is a considerable amount of difference here. Another important factor we have to understand, though for simple building calculations or even some of the simulations, we typically take a constant U value for a particular wall. Say take the same case of 230 mm brick wall. We often take a U value something between 2.1 to 2.3 watts per meter square Kelvin, and this is a single value which is used for calculation all through the year. But what happens with respect to the surface finish, with respect to the change in ambient temperature, ambient humidity, ambient air velocity, then one needs to understand that the U value is not constant, but it is dynamic all through the year. It varies from hour to hour, it varies from day to day, season to season. But for total building calculations or load calculations, say heating, cooling load, the impact of this film coefficients and the changing U value because of these ambient as well as surface characteristics is say about 4 to 5%, or still it is being researched, roughly about 4 to 5%, which is not a heavy impact compared to the other contributors. Say for example, when I want to introduce an insulation here, the effect of this versus the effect of insulation is considerably different. The insulation has very high impact compared to the change in film coefficient. So often it is ignored, but still as a scientific number this has good amount of significance in the calculation of U values. Then about convection, we often know, we always talk about air velocity and how it improves comfort. Convective heat transfer, you have a simple formula again, you have H, which is a convective heat transfer coefficient, then again A, the area containing fluid, say it can be window or it can be, say for example mechanical heat transfer, it can be the fluid by itself, then it is a temperature difference, that is delta T. This would give you the total amount of, there we referred it as Q, here we are calling P, whatever the number, it is a total heat transfer through convection. Two types of convections are there. Free convection, when the transfer of heat occurs or the movement or flow of gas or liquid occurs because of density and temperature difference. The other is forced convection, where you have a mechanical system or a pump which is forcing the convective heat exchange. This is typically happening in air conditioning system, where you have a mechanical system forcing the heat transfer or forcing the flow of fluid and subsequently the heat transfer. This, for example, can be referred to the stack effect, where the hot air rises up and the cold air settles down. This is a natural phenomena because of density and temperature difference of the air. The convection efficiency depends on the speed of fluid movement. Simple example, the more breezy the air, you get more comfortable pretty fast compared to stale air. Say you have an air velocity of 0.5 meter per second versus an air velocity of 1.5 meter per second, so the comfort level considerably improves. The next mode of heat transfer is a radiative heat transfer. It is electromagnetic waves through which the heat is getting transferred. It does not need a medium. Typically we know solar radiation, we get direct solar radiation, it passes through the space without any medium. Thermal radiation is an electromagnetic wave which includes light. Some of the radiation we are able to see, we call visible spectrum. We have ultraviolet, we have infrared, short wave and long wave infrared, and the thermal radiation varies with respect to the temperature of the emitting surface. The higher the temperature of the object, the more thermal radiation it gives off. As the temperature rises, the thermal radiation produces more short wavelength radiation. Say for example, typically at 1000 degrees centigrade, the color of light will be yellow orange and it would turn white as the emitting surface increases in temperature. We should remember the heat transfer depends on the temperature of the emitting surface and the surface area which is receiving it. There are two types, as we said, we are interested as for building applications. It is short wave infrared and long wave infrared. Ultraviolet, the ozone layer is more or less absorbing the ultraviolet radiation. As for buildings, infrared is important, short wave as well as long wave radiations are important. The direct solar radiation which is impinging on a surface is short wave radiation. The building surfaces absorb it and then after storing it starts re-emitting it. Once they re-emit in the form of long wave radiation. This is typically we refer in the form of glass, the glass houses or the greenhouse effect in buildings. So you have a glazed window, the glass is transparent to short wave radiation, it lets in short wave radiation, the internal surfaces get heated up and they re-emit long wave radiation. Now the glass is more insulating towards long wave radiation, it does not allow the long wave radiation to go out. So because of this reason, the indoor environments get heated up, these long wave radiations are trapped inside the room. Because of this you have more warmer or hotter indoor environment. So typically use of glass is not or a simple glass without treatment, non-treated glasses are not advisable in hotter regions, mainly because they trap the re-emitted long wave radiation. Radiative heat transfer can be calculated. You need a Stephens-Boltzmann constant, then the surface area and the absolute temperature of the emitting surface. We have two important terms here, one is absorption, other is emission. Often you get to see a term called absorptivity, it is expressed as A or alpha. Commonly people say the absorptivity of the material, or if you want to calculate or you want to simulate, there is always a parameter or a space where you need to enter the absorptivity of the material. And there is also another term, emissivity. You will commonly hear emissivity, the term emissivity, low emissive glasses, low E glasses. This is a emissive property. These are the two properties which determine the radiant exchange of a surface with its environment. It depends on the wavelength of the radiation as well. Say white roof versus a grey roof, or a painted surface versus an unpainted surface, a black color painted surface versus a white painted surface, a matte finished surface versus a reflective surface. So absorptivity is a main factor which determines the temperature response in the short wave radiation, and it is dependent largely on the color. This is where we talk about a white painted surface versus a dark color painted surface. We say it absorbs a lot of solar radiation. The next important property is emissivity. It determines the long wave or the thermal radiation exchange. So that is where the effect of low emissive or low E coatings come into application. Let us take a look at a quick, a small experiment that we can imagine. Let us, I have termed it a emission experiment. Imagine there are 4 containers. One is the shiny metal container, it can be like a aluminum or a JE sheet shiny metal container. Then this is a dull metal container, it is not shiny. Third is a dull black container, and the fourth is a shiny black container. Imagine you are filling warm water, similar temperature water in all these 4 containers. Say take a 10 to 15 minutes time. Now which of these containers will still have slightly warmer water and which will have cooler water? If we are able to understand this in a small scale, then we will be able to have a better clarity on what happens in the buildings. The shiny metal container would have the warmest water after 10 minutes comparatively among the 4 containers, because the shiny surface reflects the heat radiation back into the container, so not much of heat loss happens. Whereas the dull black container would be the coolest because it is best in emitting heat radiation. We have the black body radiator, so it emits a lot of heat. For that reason this shiny metal container, water in this container, retains more heat compared to the other one. Similarly, you keep the same, in the same part, that is the same vessel, you have warm water, but you are placing it equidistant from a heater. Say it is a radiant heater, you are placing these containers next to a heater at similar distances. Now which will have warmest water after 10 minutes? Now it is the other way around, the dull black container would be the warmest because it is also a absorption, it is a black body absorber, it absorbs a lot of radiant heat. Because of this the water gets warmer, or at least it is able to maintain its temperature, whereas the shiny container would be the coolest because it reflects most part of the heat, it is poorest in absorbing heat radiation. The similar phenomena happens in a large scale in actual buildings. Typically connecting whatever we have studied so far, conductive, convective and radiative mechanism, what happens through the wall? Simple conduction phenomena that we looked at first. It can happen through wall, it can happen through window, it can happen through roof, or through the ground, there can be conduction. Then the next thing is convection, where it can happen through open windows, or it can happen through mechanical system, or it can happen through cracks in the doors and windows. The third is radiation. If the ambient is hotter, there is a lot of short wave radiation going to enter through the glass or glazed surfaces, then indoor is getting heated up, you will find a greenhouse effect. Alternately, the wall is also getting exposed to direct solar radiation, it gets heated up, and then you will find the wall re-emitting into the inside. This is also part of radiative heat transfer. Similarly, the opposite phenomena happens in winter. Now looking at the types of thermal insulation. So the whole interest for us in studying these heat transfer in building envelope is to provide a better thermal envelope which can resist heat during summers, and it can enhance heat transfer during winter. It can gain more heat in winter and it can resist more heat during summer. The most common type of thermal insulation which is used or which is often referred on and off in the field is a resistive insulation. So you have always a company selling products, they say this product has very low U value or the resistance value is pretty high, R value is this much. We often talk about resistive insulation. Here the mode of heat transfer, primary mode of heat transfer which it attacks is the conductive heat transfer. So this is the first thing, because of thermal resistance there is a inertia in heat transfer. So this particular wall has a U value, now I am going to insulate it, I am going to insulate this wall, then the heat transfer, the conductive heat transfer is going to be minimized. So this is a type of resistive insulation. The second type of insulation is reflective insulation. Imagine you have a reflective coating here which is going to reflect back the direct solar radiation. In this case the mode of the first shield, this becomes a first shield. Alternately you have a wall, you have a second wall, it is a double layer wall. Simple, what happens? Now you have a air film, there is a third thing here. So this is layer 1, layer 2, 3, 4, 5, 6 and 7. So the heat transfers through 7 different layers. Now let us introduce a thermal insulation here. This becomes resistive insulation. Next thing is, for example, if I am painting this surface with a reflective coating. So if I am able to say this particular membrane is going to be a reflective coat, I am introducing reflective thermal insulation. The third or most rarely used insulation type is a capacitive insulation. Traditional architecture, India especially, have been relying on capacitive insulation. You see materials like granite, thick walls, massive earthen walls being used in buildings. They were kind of capacitive insulation. They were taking advantage of the material's thermal capacity and its density in storing heat. They were using massive walls because the wall get heated up, it stores a lot of heat inside before transmitting it indoor, and evenings when the diurnal the diurnal heat range is much larger, temperature range, the night time temperatures are pretty low. So before it gets transferred inside, it is re-radiated outside. So this particular capacitive insulation was valuably used in our traditional architecture, but modern architecture we mostly rely on resistive insulation. You have some insulation material, you can put it inside the wall, outside or in the center of the wall. Some cases reflective insulation is starting to be used now, this is also effective, but capacitive insulation, say when you use a material like concrete, typically people look at concrete as not so useful material because they think U value of concrete is high. Say imagine concrete wall of 200 mm thick or 230 mm thick, brick 230 mm has a U value of 2.1 watts per meter square Kelvin, whereas similar thickness 230 mm concrete wall would have a U value of around 3.5 or 3.6 watts per meter square Kelvin. So naturally if you do conductive heat transfer calculation, concrete wall will give you more heat load or cooling load because it is transmitting lot of heat inside. But what one needs to realize, there is a lot of difference between an insulated wall. Say for example, imagine you have a gypsum wall which is a thin sheet plus glass wool insulation 50 mm, you can manage a U value of something close to 1 or 1.2 watts per meter square Kelvin. Compare this with the concrete wall 230 mm which has a U value of 3.5. Now I am talking about two different things. First is a gypsum wall, one is a gypsum panel, and then you have insulation. Imagine the U value is 1.2 watts per meter square Kelvin. Then I have a concrete wall, this will be about 65 mm, the concrete wall is 200 mm. Here the U value is 3.5 watts per meter square Kelvin. Now this U value is 3 times of, more or less 3 times of the gypsum wall. Advantages, if you calculate conductive heat transfer, this is really advantageous. If it is air conditioned, if it is sealed, the whole thing works really in a good way. But if you are talking about a naturally ventilated space, what happens? Apart from this conductive mode, there is also a capacitive insulation, or the thermal capacity of this particular wall is high compared to an insulated gypsum wall panel. In this sense, this particular material or any massive material is able to store a lot of heat and then re-emit it back to the outside compared to what an insulated wall, thin insulated wall can do. So the third mode of heat transfer or a capacitive mode of heat transfer is really valuable. This is exactly what we were doing in our traditional buildings. We are going to look at these types more in detail along with some indices which are really useful for us. Before going into the next section, one important thing we should understand while we discuss about heat transfer through building envelope is the concept of soil air temperature. We did discuss about soil air temperature in one of the previous modules. This is a very valuable indicator. When we talk about delta T, what happens to the temperature here outside, temperature outside versus temperature inside. We were talking about TO and TI, but what is more important is what happens on the surface, what happens in this particular surface, what is a surface outside temperature and what is a TSI, what is the inside surface temperature. These two parameters are crucially important. The ambient temperature, say in summers in a hot dry climate may go up to 45 degrees centigrade. But what happens, there is a concept called sol air temperature where you have to add the effect of ambient air temperature along with the incident solar radiation which is falling on a surface. Naturally, when sun falls, the solar radiation, short wave radiation falls on a surface. It also, through radiative heat gain, it also increases the surface temperature. So the surface gets pretty hot. So when the ambient temperature is 45 degrees on a, say typically a grey or white color surfaced wall, even the surface temperature in a east or south facing wall during summer is bound to go up as high as 55 to 58 degrees centigrade. It considerably varies based on the surface property as well as the solar irradiance, and the third is the heat transfer coefficient. So this particular equation is really important. There is a factor of outside air temperature T out plus you have absorptivity of the surface. So here is where you have a white color surface versus a a dark color surface. Then the global solar irradiance in watts per meter square, the amount of solar radiation. As the amount of solar radiation goes up, the sol air temperature is going to go up. A dark color surface, then the sol air temperature is going to go up. The light color surface, the absorptivity is less, so the sol air temperature is going to come down. Then you have heat transfer coefficient for radiation and convection on the outside surface. So as this is going to increase, sol air temperature is going to come down. This has a slight effect, marginally lower effect. This is a particularly important thing. We are going to look at this further more in the next modules. One quick information I wanted to give you, as the sol air temperature increases, the discomfort hours, we talked about degree discomfort hours, the discomfort hours drastically goes up even with a different U value. The U value can be lower or higher, but as the sol air temperature increases, that is the surface temperature here is going to go up, that is delta T is increasing, the discomfort is going to considerably increase. Looking back at what we were seeing in the first slide, imagine a material with high thermal transmittance and low thermal transmittance. The heat built up considerably varies, because of which the heat transmitted indoor varies. Along with that, the time taken for heat transfer also varies. We will look at this further more in detail. This is how convective heat transfer happens. The same wall with a closed window, the same wall with an open window. How much amount of heat is gained or lost because of cross ventilation. This is about radiative heat transfer. The time taken for radiative heat transfer also considerably varies. There is sol air temperature. Apart from this, this is going to re-emit into the building and then it is going to absorb and re-emit it outside the building. So three modes of heat transfer and how it is used in buildings. So to quickly wrap up, we looked at the fundamentals of heat transfer through building envelope and we looked at few applied examples for a better understanding of heat transfer. Thank you.